Welcome to everyone. Previous class we have discussed rotational spectroscopy. Now we'll go about of vibrational spectroscopy. Vibrational spectroscopy. Vibrational spectroscopy also is we call IR spectroscopy because IR we are using. This is also called. It is also called IR spectroscopy. It is also called IR spectroscopy. So the condition is for that a change in dipole moments. Change in dipole moment should present. So let's say how I'm saying. So rotational spectroscopy, we see that like whenever this A and B molecules, let's say AB molecules, let's say this is a polar. Polar means their charge separation is there. So let's say this is more electronegative, so I put delta minus and I will put here delta positive. And so dipole moment direction is from positive to negative, so I will put these signs. Okay, so now for rotational spectroscopy, what you see that there is also change in dipole moments, that's why that is microwave active. And this for vibrational spectroscopy, this is also IR active, then we say that are comes under IR spectroscopy. So like for rotational spectroscopy, what we see, rotational, let's say it's A and B, and let's say this is delta negative and let's say this is delta positive, means polar molecules, and the rotating is from here to here. So here what we see that dipole moments means that is Q into R. Q means charge on the metals or charge on the molecules, and R is distance between these two molecules. So here whenever you are rotating a molecules, let's say what you see that here it will rotate like this, sorry, B and A. So here the dipole moment directions was like this from positive to negative, and here the direction is like this. So here that Q and R were fixed, only the change in directions were there, that's why dipole moment is changing. So for rotational spectroscopy, because dipole moment is a vector quantity, if any one will change either magnitude or directions, then dipole moment will change. So here magnitude is remain constant, Q and R is remain constant, but direction is changing because it is rotating. So since direction is changing, so dipole moment will change. So here change in dipole moments is due to change in directions. Change in directions. But wherever we are talking about of this vibrational spectroscopy or vibrational, so what this molecules is vibrating, like here this actually how it like this. Let's say this is delta positive and let's say this is delta negative, because this is the polar molecules. Now again if it vibrates, then how it will vibrate more or less like this, sometimes this or sometimes like this, means it is vibrating like a spring. So this is delta negative, this is delta positive, this is delta positive. Here we see that here the dipole moment direction is this directions from positive to negative. So here we see that unlike rotational spectroscopy, here direction is same for all the case. Means here for dipole moments, so we need the change in dipole moments for IR active. So I am looking for where is dipole moment is changing. Okay, so dipole moment means Q into R, and this is a vector quantity. So if any magnitude or directions any one will change, then dipole moment will change. It depends on two. One is directions, another is magnitude. One is directions, another is magnitude. So any one if change, then the dipole moment will change. So here the dipole moment is Q into R. So direction is not changing. We see that same directions everywhere. So direction is not changing. So direction factor is gone. Now magnitude factor. So magnitude factor means this Q and R. So here we see that charge is not changing. Here also same, here also same, because atoms is remaining same. But we see that length is changing from here to is, let's say this. Here it become high distance, it become again low distance. Means that R is changing. So if anyone will change, means magnitude changing. So if anyone, magnitude or direction, anyone will change, then dipole moment is change. So due to change in the length or the distance between the two molecules is changing, so dipole moment is changing. So here change in dipole moments is due to change in distance between two atoms. Okay, so any molecules if we see change in dipole moments, then that is maybe vibrational actives and rotational actives. But for active, for vibrational or rotational active past, change in dipole moments should be present. Okay, so now we will discuss on that how this that how that a molecules is vibrating. Let's say it's a molecules B. This is actually like this is polar molecules, so delta minus and delta positive. And this is the direction dipole moment is from positive to negative, so I give direction like this. So for simplified, I am taking as a line, let's say A and B. Okay, this is the directions. Now if this molecule is here, now you are giving any electromagnetic radiations to it, like rotational spectroscopy. You are giving that electromagnetic rotations, sorry, electromagnetic radiations to it, or I can say any electromagnetic radiations we are giving. This is the electromagnetic radiations to it. Then what happened that if these molecules had some energy, with some energy it is vibrating like this, maybe this to this, like this, it is vibrating. So whenever you give these vibrating molecules and electromagnetic radiations to it, then what happened that these molecules gain energy if that energy matches with that energy, so that it can shift to a higher energy. So what you say that in this is actually this physical spectroscopy, this is actually in quantum chemistry part. So what you say that in this quantum chemistry everything is fixed, means that energies are quantized. So it will gain that amount of energy which allow this molecule to shift to a next higher energy, means to next higher energy. Means why I am saying this next higher energy, means here that energies are fixed. Let's say this much, means here some energy is there, x, let's say 2x, let's say 3x, let's say 4x, this energy. And suppose this molecule is vibrating here and we are giving that electromagnetic radiations to here, and these molecules A and B, this molecule gain this energy, this electromagnetic radiation, actually the frequency, only if this electromagnetic radiation after gaining the energy, if it able to shift to this next higher energy. Means this energy is already fixed, this energy is already there, this energy is already there, these are the fixed energy. So it will gain that electromagnetic, means this energy by whichever you are giving by electromagnetic radiations, only that energy it helps to go to this next higher energy. If that energy is not after gaining this energy, if it is not able to reach here, suppose it is reaching here, then it will not gain that energy, because here if it go, then also there is no energy level, so again it has to return back. So it observes that amount of energy which allows her to shift to the next higher energy. So that what we say that quantized energy. Okay. So now what I'm saying that let's say this A molecules, AB molecules, this AB molecules is vibrating. AB molecule is vibrating. This is delta minus, this is delta plus. So what is that? Let's say this is heavier atoms. This is heavier, or any one is heavier atoms, and let's say this is lighter atoms. Then what will do that? This lighter atoms will vibrate, and this will means it will change its relative positions and it will remain its position. Let's say again, if you give that electromagnetic radiations, or I should take, let's say this is the heavier atoms, and whenever if you give that electromagnetic radiations, then this will fix its energy, means sorry, this is lighter atoms, so these atoms will change its relative position and remain in its place, means it will go like this. Whenever you give electromagnetic radiation, it shift to the next higher energy levels, and this atoms is remain fixed its relative position and it is changing. Again, if you give electromagnetic radiations to here, then let's say this B is fixed and this will go to like this energy. So this way also happen, or another way, let's say both atoms are lighter. This is the lighter atoms and this is also lighter atoms. And whenever you give electromagnetic radiation, then both will change its relative positions. So this both way can possible. So both way can vibrations can happen, like both change its relative positions, or here both changing its relative positions, or here if one heavier, one lighter, then the heavier one is not changing its relative positions and lighter one is changing its relative positions. So both way vibrations can happen. So let's, if you do a plot here, so let's talk about of the HCl. So here we see that Cl is heavier atoms and this is the lighter atoms. So if you say here is the energy, and whenever you say that let's say here Cl is there and here H is there. So what is the, what about a bond length, you can discuss first. Let's say any AB atoms, this is the its bond length. What does it mean? Let's say here A atoms is there, so this is A atoms, this is its nucleus, and over here that electrons are there revolving, electrons are revolving around it. And let's say another atoms, its nucleus is here and its electrons also revolving here. So now what we say that nucleus, this is the positive charge, here is positive charge, here also positive charge. So you know that positive charge, it means nucleus, and nucleus, they have the attractions, sorry, repulsions. Same charge will repulsions. Similarly, electrons have the repulsions, and nucleus and electrons, they have the opposite charge, so they have the attractions. So what happens whenever you bring the two atoms closer, then what happens that due to these two atoms, due to these two nucleus, they get repel, means here there will be repulsions will occurs, and here also due to this same electron there will be repulsions will occur, On the other hand, whenever they go far away, then this nucleus and electrons, they get attracted, and this nucleus and electrons, they are opposite charge, so they get attracted. And similarly this means that, so whenever you bring two atoms closer, then they, due to this nucleus, they get attractions, and whenever they wants to go far away, due to this electron and nucleus, they again get attracted. So they will stay at such a positions, rather attractions happen, rather repulsions will happen. That distance is called the bond length. Okay, so this is the bond length where no repulsion or no attractions is there. So this is the bond length, or also we can say that is the equilibrium position. So we can say R equilibrium. Okay, so now if we little bit what you say, pull the hydrogens towards chlorine, then what happens? This will come here, hydrogen atoms, and whenever you pull these atoms nearer to it, then due to this nucleus it get repulsed and it again push back. So again it will go to here. Again, if you more attract, if you more pull, then it will come more closer, and if it more come closer, then it will more possibly it will push. So it again it will go like this. So like this, if you more do, and here is chlorine is there. Okay, so this way that we can draw a that this way that hydrogens and chlorine atoms are vibrating. Okay, so now what I want to say here, that now I am saying that now what I say that I pull it. So actually what you say that we are not here. So actually what it is happening by itself, what happened that we are giving a electromagnetic radiations to these atoms at this equilibrium positions. Then whenever you give equilibrium position, whenever you give electromagnetic radiations, so at this time also it is vibrating. Okay, it at that time also it vibrating, and if you give that electromagnetic radiations, it gains some energy. I will explain the next. So you draw like this here. So let's say this. So at this time also, that here is, let's say here chlorine is there, here is hydrogen is there. So this is vibrating with some energy. So whenever you give that electromagnetic radiations to it, then what happened that this this here HCl is there, that is vibrating, so it gains some energy from this electromagnetic radiations, and if that energy after gaining, if it is equal to this amount of energy, then it will shift, otherwise it will not shift. So how these energies are uh, arranged like this, up to this only this energy level is there, not here is no energy levels, no here is no energy level, and no here energy levels are only here. So how these are arranged? So these are arranged by this actually given by Schrodinger equation. From Schrodinger equations we get that equations, so that will discuss more in quantum chemistry. So I'm just giving that equations. So that equations is B, that is vibrational constant, plus 1 upon 2. So that energies are arranged like this. E, that meant this arranged by these equations. By these equations, these are arranged here, not here, not here. Only here will come, here it will come. Okay. So now, what is this? This is actually omega, or you can say this is nu frequency. Okay. And this is in joule. Now, how can you say that? So this is in joule, but in in spectroscopy you will study everything in centimeter inverse. So before deriving this before discussing more about these equations, we should know one more thing, that whenever this hydrogens, if you pull here, then from this equilibrium position, this is the equilibrium positions. From equilibrium positions, we are pulling to here. So whenever you pull from equilibrium positions to this, then some force is again, whenever you are pushing towards that chlorine, then another force is there which is actually giving repulsion, so that it will go like this directions, so that it will go in this direction, right? So whenever you are pulling, then some force is applying back opposite to this. That is called the restoring force whenever you apply from this equilibrium distance. So again one force is there which is backside to this, opposite to this, whatever you are pulling the hydrogens towards chlorine. Okay. So that force is called restoring force. So that is that restoring force let's say F, that is opposite to the whatever you are pulling. So how much you are pulling from this R equilibrium to this distance? So let's say from this distance to this, let's say this is X, then that restoring force F is, so this is applying opposite to whatever you are pulling the hydrogens towards that chlorine, that is opposite, so we will put minus, and that is directly proportional to whatever the distance you are pulling. Okay, that let's say this is X distance from R equilibrium to this distance, that is called X distance. So this X distance you are pulling, and whenever I remove this proportionality constant, we know that whenever we remove proportionality constant, proportional, we have to put one constant. So I will put one constant, that is a K. So this K is restoring force constant. This K is restoring force constant, and this equal to minus Kx. Okay. So now let's go this. So for doing this energy levels, we use these equations. Now that is, what do you mean by this nu? So you know that how to calculate the nu. Nu is actually 1 2 pi K into reduced mass, and this K is restoring force constant. This K is equal to restoring force constant. That how will you derive? By this. Okay, this is the restoring force constant, and this nu is reduced mass, that we know that in rotational constant, rotational spectroscopy, that nu equal to m1 m2 m1 plus m2. Okay, so now that this, but this is in joule. So now what is say that in this nu equal to C upon lambda, because C equal to nu into lambda. So if you want this in a centimeter, because in joule, but we want everything in a centimeter whenever we are talking about a spectroscopy. So what you do, that I will divide this, then get this value, and this value is actually what? Wave number, and wave number is always in centimeter inverse. So this becomes centimeter. So if you want to centimeter inverse, then what I will have to do? I have to divide by C. Here also I will divide by C. Okay. So this one I can write nu upon C is wave number. This equal to 1 upon 2 pi C K nu. Okay. So this one I want this also energy is joule, so I want this also in centimeter inverse. So what I will do? This is E equal to what the value? B plus half nu H. Now we are discussing about of this is actually harmonic oscillations. This is harmonic oscillations. Harmonic oscillations. So we will study two type of oscillations. One is harmonic, another is enharmonic oscillations. So first we are discussing about a harmonic oscillation. So harmonic oscillation, this frequency, since we are discussing about of that oscillations, so we are discussing about of this frequency, since we are discussing about of that oscillations, so harmonic oscillation, this frequency, since we are discussing about of that oscillations, so harmonic oscillations, this frequency, since we are discussing about of that oscillations, so harmonic oscillations, this frequency oscillations. So here we call this nu, or we can say nu also, or we sometimes that is written as omega. Okay, because we are studying about oscillation, so we will say that nu as oscillations, omega. Or some books it represent as nu as itself, or some book it represent as oscillations, written omega, because we are studying about oscillation. So I will do this by putting this nu instead of omega instead of nu. Then what I write, b plus half nu omega h. Now this is in joule, so I want this in centimeter inverse. So what I will do, that we know that E equal to h nu, and h nu equal to c upon lambda. Then I want this lambda, because this lambda is wave number, that is this is equal to wave number, that is centimeter inverse. So to get this value I have to divide it here. Okay, so that's what I'm doing here, E hc. Then I also divide here also, b plus half omega h upon hc. So this h cancel, that will going to become E hc plus half omega upon c. And this omega is actually frequency, as frequency upon c is equal to, we say that is wave number, that we say right here, frequency equal to wave number. So here we are taking this as omega, then I will take omega equal to this. So here I can write this as E upon h. This I can write, let's say epsilon, that is equal to b plus, this is not nu, this is b, this is b, rotational constant, that will write b plus half, this is omega naught. Okay, so this is in centimeter inverse. So these equations we use to derive this energy levels. Okay, where this is that vibrational quantum number. Okay, and this value we know, this omega naught is, we know that is 1 upon 2 pi c centimeter inverse. Okay, so this one we will put, this equation we will put, and we will derive this energy levels. So this epsilon equal to b plus half omega naught. So these equations we will put, and we will derive the equation. Let's say if b equal to 0, then so epsilon become, this is 0, so half omega naught. So whenever this is a 0 values, let's say this is 0, or I can write b equal to 0, this value becomes how much, 1 upon 2 omega naught. Okay, and whenever this b equal to 1, let's say if b equal to 1, then E is become, this is 1 plus 1 by 2, that is equal to 3 by 2, 3 by 2 omega naught, this is become 3 by 2 omega naught. And whenever this b equal to 2, then epsilon becomes, that is 2 plus half, that is become 3 by 2, that is become pi by 2, that is going to become pi by 2 omega naught. This b equal to 2, that is become pi by 2 omega naught. And whenever b equal to 3, that is become 7 by 2 omega naught. So like this means these energy levels are arranged by using these equations. So these energies are fixed, or that is quantized, we can say in quantum chemistry, that is quantized. And this, say let's say one molecule is vibrating here, and this vibrating molecules, and if you give any electromagnetic radiations to it, then these molecules observe this electromagnetic radiations, the energy, only after observing this energy, observing this energy if this energy is equal to this energy levels, so that it can shift here, then only it will observe, otherwise it will observe that electromagnetic radiations. Okay, so if let's say this is 1 by 2 omega naught, this energy, this is the energy, this is the energy. So let's say this is the 1 by 2 omega naught, and if we give electromagnetic radiations to it, and that electromagnetic radiation is 1 omega naught, let's say it has 1 by omega naught, and by using electromagnetic radiations it observes omega naught, then how much energy it will do? That is 2 by 2, that is 2 by 2, that is equal to 3 by 2 omega naught. Then it observes this electromagnetic radiations and shift to this energy. This heavy molecules go to here. But if it has the 1 by 2 omega naughts, and we give that half omega naughts, means from electromagnetic radiations we are giving this amount of energy, then it will not observe, because after observing it getting omega naughts. Here omega naught is not here, omega naught is not lies here, omega naught is no energy level is here, so it will not observe this energy, and because here no energy levels is there, so it will observe that energy that is given by electromagnetic radiations only if after observing this energy, if it able to shift the next higher energy levels, then only it observes. Okay, now the question is, let's say molecules here, so we are using this formula B plus half omega naught to derive this energy levels. So this is, let's say this is 0, B equal to 0, this is B equal to 1, this is B equal to 2, this is B equal to 3, this is B equal to 4, and this is, this is how much value we are getting, 1 by 2 omega naught, and this is 3 by 2 omega naught, this is 5 by 2 omega naught, and this is 7 by 2 omega naught, this is 9 by 2 omega naught. This is energy. Okay, so now what we see here, that whenever you giving that electromagnetic radiations to it, so after getting electromagnetic radiations, it can shift to here, because it has to shift that next higher energy level, or it can also shift to here, or it also can shift to here. So that's the confusion. So for that, selection rule says came, but that this means after experiment what they found, that it will shift only this energy levels only, it will not shift from here to here, means that delta B is equal to plus minus 1 only. It means that delta B is can't be, it can be plus 1 or it can be minus 1. It means delta B means B final minus B initial, so it can be from 0 to 1, so final is 1 to 0, that is equal to 1, but it can't be delta B, let's say from 0 to 2, means final is 2 minus 0, 2, it cannot be, delta B can't be plus minus 2, can't be plus minus 3. Okay, so it can be only plus minus 1, like rotational spectroscopy. So it can shift only from here to here, or it may also shift from here to here, it also may shift from here to here, where here also delta B is plus minus 1. Okay, or it can be go from here, that is delta B equal to minus 1, but it cannot shift from here to directly here. Okay, so that we have discussed in rotational spectroscopy also, same selection rules apply here also. Okay, now one more things here, that interesting things we got here is that here you see that whenever I will draw both the things, whenever I am drawing for rotational spectroscopy, that energy levels, rotational spectroscopy, what I found that how we'll draw rotational spectroscopy that we already discussed. Let's see this energy levels here, this energy levels here, this energy levels here. Molecule is rotating like this here, AB is rotating like this, and here to derive this energy levels we use that equations, that is Bj j plus 1 energy. Okay. So what we see that here, let's say this is B, sorry, here j equal to 0, j equal to 1, j equal to 2. So I can do this. So another is here, this is j equal to 0, j equal to 1, j equal to 2, j equal to 3, and j equal to 4. Here molecule is there, AB, and that is rotating. Okay. So whenever j equal to 0, we see that E is equal to 0, sorry, that is B, and 0, 0 plus 1. That we see that E equal to 0. And whenever j equal to 1, we see that E equal to 1. That is, we see E equal to 2B. So here that energy we are getting first, that is equal to, here we are getting that 0 energy, here we are getting that 2B, like that. Here we may be getting 6B, and here we are getting that 12B, and we are getting here 20B, like that. When we put the j value here 2B, and when j equal to 2, we say that E equal to, that is 2, and that is 3, that is 6B, like that, 12B, 8B, like that, for rotational spectroscopy. So whenever j equal to 0, we see that energy is also 0. It means on that, whenever rotational constant is 0, then molecule is not rotating at all. Okay. Whereas for vibrational spectroscopy, what you see here, whenever B equal to 0, whenever B equal to 0, then also we have some energy. It means that whenever there is no means, what you said, whenever B equal to 0, then also some energy is there. So there also some energy is there, means on that time also molecule is vibrating. Means if you are not giving any energy to the molecules, then also it is vibrating. But whenever for the rotational spectroscopy, whenever you are giving no energy, means when j equal to 0, then it has a 0 energy. It means it is not rotating at all. But for vibrational spectroscopy, if you are not giving any energy, and if the temperature is very, very low, then also it has some energy. B equal to 0, then also it's some energy. So it says that for vibrational spectroscopy, even if you are not giving any energy, then also still molecule is vibrating. It is not stopped. It is not at rest. Okay. But for rotational spectroscopy, it may be at rest, because at j equal to 0, there is no energy. So at that time, the molecule is at rest. But vibrational spectroscopy, the molecule is always vibrating, because at B equal to 0, it has some energy. So this B equal to 0, it has some energy, that is 1 by 2 omega naught. So this is called 0 point energy. 0 point energy. Because this molecule is never at rest, it always vibrating. So that the lowest energy which is always present, that energy is called 0 point energy. Okay. And one more thing, if you notice between these two spectroscopy, this is the harmonic oscillations. Another we will study that anharmonic oscillations. In harmonic oscillations, if you observe it, then 1 by 2, and then 3 by 2, if you they are different this energy levels, but you found that 3 by 2 omega naughts minus 1 by 2 omega naughts. So this is actually omega naughts, because 3 by 2, 1 by 2, 2 by 2, that's 2 omega naughts. Similarly, if I do for 7 by 2 and pi by 2 omega naughts, 2 omega naughts minus pi by 2 omega naughts. Again, you will see that omega naughts, it means that and the difference between the two energy gap is always constant. Here also 1 omega naught, here also 1 omega naught, here also 1 omega naught. It means I can say that here I will draw these energy gaps are always equal, means the energy this gap and this gap, this gap, they have equally spaced, means that energy gap are equally spaced. But if you look about of the rotational spectrums, what you see that here is from this difference is 2b, and whenever here you go, here is 4b, and whenever here you go, it will again 6b, and whenever you will go, here you will get 8b, means it is continuously increasing from if you go to the higher energy levels. It means I can so if I draw this picture, then what I found, just a minute. It means what I found that for rotational spectroscopy, if I draw it, rotational spectroscopy, what I found that if you draw this picture, then this space is, let's say here, this is b equal to 0 and this is b equal to 1, and whenever you will go b equal to 2, and it will become 3, and whenever you go higher, then this is increasing, means from here this space is increasing whenever you go higher and higher and higher. But whenever you this is for rotational spectroscopy, and whenever you're doing about of harmonic oscillations, what we're seeing here that energy gaps are equally spaced. So if I drew here is, so here if we say this is 0, they are equally spaced, means each distance are same. But here whenever you're going higher, it will be increasing. Okay, so that is the difference between the rotational spectroscopy and for harmonic oscillations. So next class we will discuss about of anharmonic oscillations, and we discuss about of the diatomic molecules. So today up to this, thank you.